And now we're going to encounter perhaps one of the most amazing part of our semester here in Calc 1. We're going to talk, of course, about the Fundamental Theorem of Calculus, Part 1 and 2. They actually sandwich together. They're one big fundamental identity. It's really, really cool, and it really helps us with the future of our calculus experience in college and beyond, okay? So the first thing we're going to do, as many people online will do, and I've sent you to see them actually, is let's take a look at the proof of the fundamental theorem of calculus. What you want to do, though, is you want to write out what this guy says. It says, let f of x be continuous, okay, on some closed interval a, b. Now, we've been talking about definite integrals over a closed interval a, b, and we're talking about areas and limits and all that stuff. But look what this one says. It says, then, if you define a function, g of x, equal to the definite integral from a to x of some dummy variable f of t dt, okay, dummy variable, they need to call it other than x, so they have to use another letter, so they chose t, on a less than or equal to x less than or equal to b. Take a pause here. What are they talking about? Oh, a definite integral. What? Okay, there's a function. I got you. We're going from a to b. No. We're not going a to b. Now, we're continuous on a to b, but this particular function is saying, I want you to be the definite integral from a to anywhere I tell you to go between a and b. Okay, so that's the definition of g. Is if you want to think of it in terms of areas, then it would say wherever you want me to go, I'll calculate the area under this curve. So, and it could be under the curve, it could be positive, it could be negative, but I'm going to be calculating the definite integral from a out to wherever you want me to go. Okay, it says it's saying that this function is also, it's saying continuous on the closed interval a, b, and it's differentiable on a to b, okay? And finally, and this is the big punchline, let's write it bigger, g prime of x is equal to f of x. Okay, so this theorem is saying if we define a function to be a definite integral function of a given function little f, then if we define that function that way, then our derivative is little f, which is like, wait a second. So you're talking about a definite integral ties into, say, what we call an antiderivative of f, and that's the thing. That is true. If you want to find a definite integral, you're going to be searching for the function's antiderivative, and we're going to see examples of that, not in this video, but in the next one when we do the part 2 of this theorem. So the proof of the theorem goes along the lines of, well, let's study what this guy is. So in other words, they start pursuing the following. They go, well, g prime of x is the lem as h goes to 0 of g of x plus h minus g of x all over h, like so. So it's a straightforward thing. So they're going to look for in this proof, what does that look like? Okay, so they make it. They make a definition of that. So they build the derivative. Okay, x and x. So we're going to say let x and x plus h be in this interval a to b. Okay, and then they go, what is g of, now see what they're doing, they're building this derivative. They're going, what is g of x plus h minus g of x? Anyway, what does that represent? Well, here comes another picture. Here's f again, and a, and b, and here I go with another marker. Let's go out to x, call that x. Let's go a little bit farther, call that x plus h. And when you take the, well, when you do g of x by itself, it's this guy. But if you go g of x plus h, it goes a little bit farther out. And so what happens is you have to introduce another color and say, the difference between the areas is right there, okay? So a way to say that is to say it's equal to, let's write it out what it means first. It's equal to the antiderivative, or I should say, the definite integral from a to x plus h of f of x dx minus, by definition of the function, the integral from, or the definite integral from a to x only of x plus h dx. And by looking at the picture, we can agree that g of x plus h minus g of x is really the antiderivative from x to x plus h only of f of x dx. And you can pause it and look at the picture and say, is that true? I think it is, after perusing it a while, okay? So if you wanted to, what you could do if you wanted to build this derivative is you can go, well, that then implies that g of x plus h minus g of x, and I am following the proof, I forget what page it's on, but it's in your textbook, divided by h is equal to 1 over h, same antiderivative x, or same definite integral. Okay, so this is where we are right now. All right, now here's the thing. We have in our past something called the extreme scream. No, I'm sorry, that's Knott's Berry Farm, I think. The extreme value theorem. And it's interesting because when I watched a little bit of Khan Academy go after this proof, and I was going to say watch this guy, he uses the mean value theorem for integrals, which is for us anyway in the next chapter. So I thought, well, I could let you watch that without knowing that theorem, and the theorem's pretty straightforward, or we could just follow Stewart's proof here, at least the one he publishes in his textbook, and that's what we're doing now. So the extreme value theorem is going to look, okay, let me look at this guy, from x to x plus h. If you've got a continuous function, then the function f has got a maximum and a minimum. So the function f has an absolute max. Let's give it a name. Let's say it's a f of like u is equal to, well, the way you go with the letters, I think if I follow the letters in the book, I think it's something like v is equal to capital M. And f of u equals little m, and that's going to be, according to this theorem, there definitely exists, it has an absolute min. Okay, so on this interval, you have an absolute max and min. So what it's saying is that, let's see, f of u is less than or equal to f of x is less than or equal to f of v for all x in the interval x to x plus h. Okay, so we're getting somewhere. Watch out. Here we go. So, therefore, we have a property 8, number 8, of the definite integral, which is something we covered in a previous video. It says that if your function is bounded above and below, then you have the following. You just go, remember it goes something like this. It goes little m less than or equal to f of x less than or equal to big M implies m b minus a less than or equal to the integral from a to b f of x dx less than or equal to capital M times b minus a. Now, that's a property, but in our case, the lettering in the number, I'm running out of room. Uh-oh, that's not good. The lettering changes on you. So what happens is, in our case, it is f of u times little h is less than or equal to this integral x to x plus h of f of x dx, which is really g of x, is less than or equal to f of v times h. So therefore, f of u is less than or equal to 1 over h times this integral. Guess what that is? X plus h f of x dx less than or equal to f of v, which means basically another way of writing it is that f of u, I am out of room, I have f of u is less than or equal to g of x plus h minus g of x all over h less than or equal to f of v. Okay, here's where you let h go to 0. Okay, and you look at an interval and you go, okay, here's x and here's x plus h. And in this interval is the max and the min somewhere. So this could be u, where the max occurs, or the min, and this could be where the max occurs, v. But as h goes to 0, this gap gets smaller and smaller and smaller. And it forces f of u, it forces u to go to x, and it forces v to go to x. And as h goes to 0, this turns into f of x, and this goes towards f of x also, because u and v are going to x as h goes to 0. Well, what does that force this guy to do? It forces him also go to f of x. But as I cram it in here, what this little guy is saying is the derivative, and I'll write it on the next page. So it's saying basically the lim as h goes to 0 of g of x plus h minus g of x all over h is actually f of x. And we're done, because this left-hand side, this is the definition of the derivative, and we have it. That's the first part. The first video, this video here, of 2, basically will mess around with this idea. If you define, derivatives defined as definite integrals, if you define a function as a definite integral, we know that its derivative is the function inside, that is the integrand. Okay, so looking at these problems, you're going to see homework problems like this. You ready? Okay, so find the following derivatives. And you might be going, wait a minute, I thought I was integrating. Well, hold your horses. The first part of the theorem is, I have now, look at this guy. We have defined g of x to be this antiderivative. Okay, and if you want a picture, you can take a picture of it. And this is whatever function that is. This is tan inverse of t, or if you want x over 2t. And we're integrating from 3 to, x. So it's a function. G is a function defined as a definite integral involving another function. So when they say find the derivative, all you have to do is the following. The derivative, get rid of some of this extra stuff, the derivative is right in here. Because it says, if you define g that way, your derivative is the integrand. So what you can do is simply say, my derivative is this, tan inverse, put the x in there, all over 2x. And it doesn't matter if you're starting at 3 or 5 or 1,000,000. If you're defined to be this definite integral, then your derivative is the integrand itself. Let's try another one. H prime of x, okay, if h is defined this way, oh, this is weird. This is one I got from the book, I think. You see how the limits are switched? Switch them back. Okay, 5 to x, natural log of 1 plus t dt. But if I switch the limits, what have I got to remember to do? I got to change the sign. That's right. That's another property from definite integrals. If you switch the limits, you got to change the sign. So therefore, now you can take the derivative, and the derivative is minus this function, natural log of 1 plus, guess what? X. Done. So that's what the derivative is equal to. A negative. Okay? 2 more. They're quick. This one. Find the derivative. Okay, it's defined as a definite, but what's going on up here? We're composing this. What the heck is that? Okay, let me remind you. Okay, consider a function that says, I don't know, h of x is the square root of 3x cubed plus 2t, or 2x, or something like that. Okay? Well, how would we derive that? Well, h prime would be, I derive the outer function, which is 1 over twice the radical, right? 3x cubed plus 2x. But then I hit it with its derivative, and its derivative, of course, is 9x squared plus 2. Everyone knows that, gosh. Well, guess what? This is done the same way, except that the outer derivative, if you will, f prime, the outer derivative is the actual definite integral, and inserted into it is this inner function. So you just simply go, the derivative is x cosine, whoops. What do we have to do? We have to apply the inner function to it, don't we? So it's going to be 3x cubed plus 2x times cosine of same, 3x cubed plus 2x, and then times the derivative of that, which we found to be 27x squared plus 2. There you go. All right. What? I know. So it's the same thing that we do here, right? We derive the outer function, apply the inner function to it, and then hit it with, multiply it by its inner derivative of the inner function. Same story. This last one we do. Let's do this one together. We have g of x. You know what I'm going to do first? Yep. I'm going to switch the limits of integration so that this guy is defined correctly. All it does is it's written the way it is, therefore you're integrating backwards, so you're going to get a negative. And then you have the square root of 1 plus t squared, etc. Okay, so what is g prime? It is, the outer function is the definite integral. It's going to be a minus square root 1 plus, but then what happens? You take stuff times derivative of stuff. I'll put it in color this time. I should have over here. This should be this, and then its derivative. I'm going to go a 1 plus sine x, and then squared, and then the derivative of sine is cosine of x. And this guy's done. Okay? All right, so that's the end of this first video on the fundamental theorem of calculus, and we'll get to the real nitty-gritty in the next video. Okay, see ya.